In today's class, we'll be looking at enolate formation in organic compounds. Before we proceed, we should understand what organic compounds are. These are compounds of carbon. In organic compounds, carbon can either bond with itself covalently, and carbon can bond with hydrogen, carbon can bond with other atoms such as oxygen and halogens. Examples of these organic compounds, we have carbonyl compounds, which are aldehyde and ketone. We have alkyl, we have esters, we have carboxylic acid, we have amides and such likes. In these organic compounds, we have alpha hydrogen. These alpha hydrogen are acidic hydrogen. They are hydrogen contained in carbon that is connected to carbonyl functional groups in aldehyde and ketone, or that the hydrogen connected to carbon that is linking halide in alkyl halides. Because of the acidic nature of those alpha hydrogen, they are abstracted by a base, a strong base to be precise, and they are very reactive in nature. This alpha hydrogen is very important because it is essential in formation of enolate ion. An enolate ion is a negatively charged intermediate formed in organic chemistry, meaning that is an intermediate, is a precursor for preparation of other compounds. They are formed when a base abstracts this alpha hydrogen in a molecule containing carbonyl functional groups. The compounds that can form this enolate are, like I said, carbonyl compounds, which can be either aldehyde or ketone, malonic esters, which are called malonate, acetoacetic esters, which are called acetoacetate. Bases used to abstract this alpha hydrogen are strong bases, such as sodium methoxide, sodium ethoxide, potassium tertiary butoxide, or sodium hydroxide. Now, in generation of an enolate ion, this base is going to take this alpha hydrogen as seen on the slide, and then the bond between this carbon and hydrogen is going to condense on carbon, leaving negative charge on carbon. This is what we call enolate ion. When enolate ion is being formed, it is essential for it to be stabilized. How is it stabilized? These enolate ions are stabilized by resonance. In this example, we are going to use pentan 2,4-dione. We see that this compound is going to have two keto functional groups. Because there are two keto functional groups, our alpha carbon is a carbon in between these two carbonyl functional groups because it is the most acidic. The one at the terminal are acidic, but the most acidic is the one in the middle. Now, when this enolate ion, which is the middle structure, are formed, we can stabilize in two ways. Either stabilize by moving the negative charge to the right or moving it to the left, meaning that we are going to have three structures. Two are resonance and one is the main enolate anion. Now, when you're having a compound that bears only one carbonyl functional group, your stabilized form will just be one. But because this compound has two own, so we're going to have two resonance stabilized plus original enolate, making it three structures. One of the benefits of this enolate is to form an enol. Protocol of moving from keto to enol is called tautomerization. Tautomerization is defined as the removal of hydrogen atom from one side of a molecule with its corresponding or concurrent addition of that particular hydrogen removed to the other side of the molecule, meaning that I'm taking hydrogen from side A and in the molecule, and I'm putting that hydrogen at side B of the same molecule, forming an enol. A typical example of tautomerization is formation of enol from keto compounds. This is a typical example as shown. Now, remember the compound we talked about in resonance stabilization is 2,4-pentane-dione or pentane 2,4-dione, which is the compound we are having here. Now, from this keto, I'm going to form enol. Remember, looking at the keto, our keto have 2 alpha hydrogen, and my enol have 1 alpha hydrogen. The other hydrogen has gone to form bonding with oxygen. That is where we form the enol. So in that case, hydrogen atom is removed from where it is as alpha hydrogen, and it's been translated or is being transferred to another site where it's going to form an enol. So that's why we move from keto to enol. Remember, enol is unsaturated alcohol. So that site has unsaturated because of double bond. Because when this alpha hydrogen is going to be abstracted, the bond is going to condense on carbon, and by resonance there will be movement before we form our enol. In upcoming slide, we are going to understand how this enol is being formed. Now, when this enol is formed, there's another thing that happens. Hydrogen intramolecular hydrogen bonding is also created in the compound. Why? Because this compound contains 2 ketone functional groups. So when an enol is formed, it means that there is a tendency for this hydrogen that move from alpha hydrogen to hydroxyl hydrogen. This hydrogen is going to connect to the other oxygen from the other carbon, forming intramolecular hydrogen bonding. And this enol can also be resonance stabilized. Remember, the first one we stabilized was the keto. Now we are stabilizing the enol. In stabilizing enol, the lone pair of electrons is going to move. So the movement will be in clockwise direction. As it's moving, the conjugated double bond is also going to move, while the double bond connected to oxygen is going to condense on oxygen, generating negative species. In this case, we are going to form a resonance stabilized enol. The keto enol compound of 2,4-pentadione can be stabilized by resonance. Looking at the equation, you can see that the lone pair of electron and oxygen of the hydroxyl, which is of the enol, is going to move in clockwise direction. When this lone pair of electron is moving, the conjugated double bond is also going to move by resonance. As it's moving, the double bond connecting to oxygen of the keto is also going to move, depositing negative charge on oxygen of keto. Why the oxygen of hydroxyl? Because the lone pair is moving. Arrow is moving from lone pair, is going to bear positive charge. At the end, we are going to have a resonance stabilized keto enol compound. This keto enol can be generated via base or acid catalyst. Remember, a catalyst is a compound that facilitates reaction and at the end regenerated. Now, the catalyst in base can be sodium hydroxide. In this case, remember, it can be sodium hydroxide, it can be sodium ethoxide. Now, in this case, the common base is sodium hydroxide. Sodium hydroxide is going to abstract this alpha hydrogen, forming an enolate. Remember, when it abstracts this alpha hydrogen, it's going to form water. Now, because it's still in the system, this enolate, being unstable, is going to take this hydrogen back to stabilize itself, forming enol tautomer, while the base is being regenerated. In the same manner, in acid catalysis, the acid used here is hydroxonium ion. Now, in the keto tautomer, the hydroxonium ion, which is acid, is going to acidify the keto tautomer. This keto tautomer being acidified now means that the hydrogen is going to come on oxygen, forming a positive species because the valency of oxygen has been exceeded. Now, because when this hydroxonium ion loses hydrogen, is going to form water. This water is acting as a base here just like we did in base catalyze. So this base being water is going to take away the acid hydrogen, which is the alpha hydrogen, from itself. When it does, then the bond is going to also stabilize itself by resonance, forming an enol tautomer, and the acid be regenerated. Now, this acid or base catalyzed interconversion can be employed in forming our keto and enol forms of compounds, meaning that I can either use acid catalyzed or base catalyzed in forming my keto enol compounds. From this slide, you can see our acetaldehyde, the keto form and enol form. Acetone now, this percentage is probability, meaning that the keto form has higher percentage of probability than the enol. If you look at the arrow, it's telling us that the keto has higher percentage. In acetaldehyde, we have 100%, meaning that the enol is negligible. In acetone, which is a ketone, the keto has higher than 99%. So even in cyclohexanone, meaning that the keto tautomer has higher probability in synthesis, in feasibility, than the enol tautomer. The essence of enolate is as an intermediate in synthesis of some complex organic compounds. So in the next class, we are going to look at how to optimize this enolate in synthesizing organic compounds. So see you in the next class. Thank you.